Alright, in this video we're going to look at a free response problem related to one of Kepler's laws. So it says a student is given the set of orbital data for some of the moons of Saturn shown below and is asked to use the data to determine the mass of Saturn. Assume the orbits of these moons are circular. So let's pause for a second and just review the physics behind this situation. So I drew a picture here of, we'll call it Saturn, and Saturn has a lot of moons, and so they just picked 4 of them. So I drew 4 moons all orbiting Saturn here. So the first question says, write an algebraic expression for the gravitational force between Saturn and one of its moons. So I'm supposed to draw or come up with an expression between the force acting between Saturn and one of its moons. So I'll pick the closest moon. So there's a gravitational force acting between the center of Saturn and the center of one of its moons. And quite simply, that gravitational force is, or that force is the gravitational force. It's gravity that holds those moons into orbit. So that's the gravitational force between Saturn and one of its moons. This would be Saturn and a different moon, but basically it's the gravitational force. So it says write an algebraic expression. That's another fancy word for write an equation that shows the gravitational force acting between Saturn and one of its moons. That's equal to the universal gravitational constant, that's the 6.67 times 10 to the minus 11, and then it's the mm over d squared. But the m, a lot of times we use capital M when we're standing for the mass of a planet, and we use a lowercase m when we're standing to stand for the mass of a smaller thing, or the moon. And then over d squared would be appropriate, but a lot of times we write it as an r squared. So whether it's d squared or r squared. So quite simply, that's what they're looking for. And we don't necessarily recognize this yet, but they're kind of guiding me to what I'm going to need to know to solve this problem. So use your expression from part A and the assumption of circular orbits to derive an equation for the orbital period t of a moon as a function of its radius. So this is a derivation that has 2 parts, part 1, part 2, and part 1 is based on this, and part 2 is based on circular orbits, and it derives us an equation that has a t and an r in it. And we're not going to go through that derivation right now. It's in unit 7. We'll fill that in later. So now that we just derived that, though, it would have led to this equation, which is Kepler's third law, that says t squared equals, I want to make sure I write this down right, 4 pi squared over g m and r cubed. All right, let's explain this equation. So capital M is the mass of the central body. That's going to be the mass of Saturn. And that's what we're actually trying to find, is the mass of Saturn. And you can find the mass of the central body if you know the period and the radius of some things that are orbiting it. And we have t values and r values for 4 different moons. So r would be the distance from the center of Saturn to the center of the moon, and t is the period of a moon. Period is the time it takes the moon to orbit Saturn. So you can see that moon 1 has a small radius and it's probably going to go around Saturn a little bit faster, etc. And so knowing that makes my data table a little bit more meaningful here. So which quantities should be graphed to yield a straight line whose slope could be used to determine Saturn's mass? So I'm trying to get a straight line, so I'm going to write down y equals mx plus b. So there's not going to be a y-intercept. And so I reasoned out to myself that I should put the period squared on the y-axis, and I should put the radius cubed on the x-axis, and then my slope will be equal to 4 pi over gm, and I can use that relationship to find m, which is the mass of the moon. So Knowing that, I'm going to go up here, and this is going to be my x column, and this is going to be my y column. So for that reason, I'm going to put r cubed here, r cubed. And r is in meters, and if I cube it, then I'm going to have meters cubed. And t squared is going to be on the y-axis, and that's in seconds, so this is going to be seconds squared. So I'm going to take a second, and I'm going to type these values in, and I'm going to write them in my chart. Okay, I did that. And I rounded off to a couple of decimal places because those were the values that they gave me there. And I noticed something, that these are all to the 25th power, except that's to a 24. And these are to the 10th, and that's to a 9. When I graph these big awkward numbers, it's going to be a lot easier if they have the same power. So I'm going to take 6.33 to the 24th, and I want to rewrite it times 10 to the 25th power. And so I'm just going to move my decimal point over, and that's going to be 0.633. So I'm going to replace this with the value that I just wrote up here. So now they're all to the 25th power. And you can see that I'm graphing like 0.6, 1, 2, up to 5, and that's going to be a little bit easier for me. And the same thing over here, I'm going to change this one to times 10 to the 10th power by moving it to 0.663. And then I'm going to scribble this one out too. And we'll put this one here. Okay, so jumping down to part D, we did this. Complete the data table by calculating the two quantities. Label the top of the column, that's the r cubed and the t squared, including the units. They're going to give you a point to make sure that you did meters cubed and seconds squared. All right, we're ready to roll on to the next page. So on the next page, it says plot the graph on the axes below. Label the axes with the variables used and appropriate numbers to indicate the scale. So this is just kind of annoying, but they want to make sure that you can graph super, super big things. So we are graphing t squared over here, t squared, and that's going to be in seconds squared. And we're going to graph radius cubed, and that's going to be in meters cubed over here. But here's the secret of how to graph really awkward things. So on my x-axis, they're all to the 25th power. So I'm just going to go times 10 to the 25th power. And then, since I wrote that there, I only have to graph like 0.6 up to 5. So I can go 1, 2, so this would be 1, 2, 3, 4, 5, and 6. And now it's going to be a little bit easier to graph those numbers. Now I'm going to do the same thing to the y-axis. We'll write down times 10 to the 10th power. And let's look at those values. They go from 0.6 up to 5 point something. So I can do the same thing. So they actually gave me a really convenient graph to do that. And then the last one's a 6. All right, so now I have to plot my points. I'll plot mine, you plot yours. Okay, I plotted my points. I made a mistake there. We'll ignore that. And I sketched my best fit line. So it looks pretty linear. So that looks good. All right, so it says, using the graph, calculate a value for the mass of Saturn. So if I wanted to do this from the graph, again, I'm talking to myself. I graphed t squared and r cubed. And that tells me that the slope of this line is going to be equal to 4 pi squared. Oh, let's take that back. That's, yes, that is a squared. It's supposed to be a squared. 4 pi squared. I realize I did not write the squared over here. Let's throw that in. All right, so 4 pi squared over gm. So the issue is I have to find the slope of this line, and that's what they're actually testing you on. So they want to make sure that when you find the slope of a best fit line that you understand that you cannot use data points. Otherwise, you're like kind of saying that my data points define the best fit line, and I'll exaggerate my story. What if this was one of the data points? It's really a bad one. And this was one of the data points, and it's not a very good one either. If I use the data points, then I'm saying that this is the best fit line, which it's clearly not. So you cannot use data points. I have to pick any 2 points that I want on my best fit line. I'm going to pick this one because it goes right through the box there, really nice. And I'm going to look for another one that kind of goes through the corners here. I don't have a great one. It kind of sucks. All right, I'll pick this one. Okay, so I'm going to do rise over run with this. So I can see that I have 2.2. So I'm going to have 2.2 times 10 to the 10th minus 1.0 times 10 to the 10th. And then over here, this is going to be 2.2 times 10 to the 25th minus 1.0 times 10 to the 25th. So I'm going to calculate that slope value. So I didn't show you that. Please make sure you find my correction that I did not square the pi over here, and I also did not square it on the first piece of paper, so I added that over there. Alright, so I have a slope value of 1 times 10 to the negative 15. So I'm going to go over here in the slope value, so 1 times 10 to the minus 15 is going to equal 4 pi squared over g, that's 6.67 times 10 to the minus 11, times capital M, and capital M is going to be the mass of Saturn that we are solving for. So let's see what we got. Alright, I just number crunched and I got 5.92 times 10 to the 26th. And that was determining the mass of Saturn from my graph, which had a lot of, I'll say, subjectivity to it, and that I had to sketch a best fit line. I had to kind of estimate these values. And maybe a better way of finding the mass of Saturn would be using linear regression. So to do that, I'm going to have to put the values in my calculator. And I'm going to put the r cubes in for my x values and my t squareds in for my y values. So let's take a second and let's do that. Okay, so I have my data in. Now let's do my linear regression. And what do I get for the slope? So I'm going to write in some of my extra space here. I'm going to write here on the back. Alright, so I have t squared equals 4 pi squared g over m in r cubed. So my slope is going to equal, since I put this on the y-axis and this on the x-axis, my slope is going to equal this. So 4 pi squared over gm. And my slope value is 1.05 times 10 to the negative 15, which, by the way, that's not too bad from what I got from my graph over here, because I had a 1 times 10 to the negative 15, but it's really 1.05 equals 4 pi squared over gm. And let's figure out what m equals now. So m is going to equal 4 times pi squared divided by 1.05 to the negative 15 power. Then I'd have to divide by 6.67 to the negative 11. And my actual mass of Saturn should be 5.64 to the 26. So the mass of Saturn is 5.64 times 10 to the 26th kilograms. And I'm going to write that in here so I can keep that. So the mass equals 5. I wrote that wrong on my sheet. 64 times 10 to the 26th kilograms. And I'll circle that. So we were off a little bit using our graph. Again, my point is that either one of these is correct, but you have to tell somebody how you're getting the answer. I'm using my graph and then everything is a little bit subjective, or I'm using linear regression and I get that. And if I had time on my exam, I would actually do both to show that I can do that both ways. All right, I hope that one helped. Thanks for watching.